This is problem number 9 from section 3.1. In this problem it says compute the right hand and left hand derivatives as limits and check whether the function is differentiable at point P. So remember, if we look to see if it's continuous, so is it continuous? That's not what they're asking us for in this problem, but it's good to start this way because if we're looking to see if it's continuous, we always take the limit as x approaches 1 from the right, and that would be of this function, y equals x plus 2. So we're going to say limit as x approaches 1 from the right for x plus 2. And then we do the same thing, limit as x approaches 1 from the left for this function, which is radical x plus 2. And in either case, when we plug in 1, we get 1 plus 2, which is 3, and we get root 1 plus 2, which is also 3. So these are equal. So is it continuous? Yes. But they're not asking us for whether or not it's continuous. They're asking us if it's differentiable. Well, the same idea is going to apply for derivatives. Let's take the derivative on the right side, and let's find the slope at that point for the right side. And let's do the same thing for the derivative on the left side, and let's find the slope at that point. And if those slopes aren't the same, then it's not differentiable. So here's how we do that. We say limit as h approaches 0 from the right, and that's for this function here. So we're going to do, we'll write it right here, y equals x plus 2. So I have f of x plus h minus f of x all over h. I plug in the x plus h, so I get x plus h plus 2 minus the original function, which is x plus 2 all over h. And I end up with limit as h approaches 0 from the right. Limit as h approaches 0 from the right. Distribute there, I get x plus h plus 2 minus x minus 2 over h. Cancel, 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 cancel. We're left with h over h, which gives you 1. And I don't need to plug in now. I'd plug in the x value. So what's the slope at x equal 1? Well, the slope is 1. So I don't really need to plug that in. I can say that though. Slope at x equal 1 is 1. Now let's find the limit as h approaches 0 from the left. Well, that's going to be found by doing f of x plus h minus f of x all over h, which is going to give you root x plus h plus 2 minus the original function, which is root x plus 2 all over h. So this is going to equal the limit as h approaches 0 from the left. I'm going to distribute the negative, so I end up with root x plus h plus 2 minus root x minus 2 all over h, which equals limit as h approaches 0 from the left. The 2's cancel, and I'm left with root x plus h minus root x all over h. Now, when we're in this spot, we usually use the conjugate, so I'm going to multiply by root x plus h plus root x over root x plus h plus root x as well. When you multiply by the conjugate, you get limit as h approaches 0 from the left. I take this first root times this root, so I'm essentially got distributing right between two binomials, and I get x plus h. Now notice I take this root times this one to get the negative. I take the positive part times this one, I get a positive of the two roots and a negative of the two roots. They cancel out. So I'm not actually going to write those because they're going to cancel. So then we just do the in terms, negative root x times root x, and we get negative x. And then on the bottom we have h root x plus h plus root x. We go ahead and cancel the x's. We have h over h root x plus h plus root x. Cancel the h's and we end up with limit as h approaches 0 from the left of 1 over root x plus h plus root x. I plug in 0, that h cancels, I'm left with root x plus root x on the bottom, which is 1 over 2 root x. So the derivative, which we could say for the left side, so left side derivative is equal to 1 over 2 root x. Now the slope at x equals 1 is going to be 1 over 2 root 1, which is 1 over 2. Now notice the slope at x equal 1 on the right side is 1, on the left side it's a half. So because our slopes are different, no, it's not differentiable.